Today, let us start with the next module. This is about your module 3. So already we completed first module, second module, and the fourth module is completed. So I will share the notes of fourth module shortly, the material. Next, let us go for module number 3. So, in the previous classes, we studied about the sources of power reduction. The sources of power reduction as different sources are there. Like if I want to say, static power dissipation and dynamic power dissipation. So, in the dynamic power dissipation, we had some different dynamic power dissipations was the sources. The one will be switching power dissipation, then one more we have short circuit power dissipation, then one more we studied as the leakage power dissipation. Now okay, we got or we might have studied all of the power dissipation techniques only. Power dissipations we studied. Now how to minimize those powers, like how to minimize the switching power dissipation, how to minimize the short circuit power dissipation, how to minimize the leakage power dissipation. So now here elaborately we are going to study about how to minimize the leakage power, So what are the different techniques are available? Okay. So to put on to this topic here, to minimize the leakage power, like will be in two mode, because normally the circuit will operate in two ways. The one is like in a active, the one more will be in the, that is active or runtime. During runtime I can say active. The another one will be not active, or I can say will be in the ideal state. Okay, active state or the ideal state. So active state is when it is working, when the circuit is working. Ideal doesn't when the circuit is not working. So these two the scenarios we have to study. The first the scenario we are going to study when the circuit isn't working in condition, how we can minimize the leakage power. Then what are the techniques are available, that only we are going to study. So now in this the first thing is in the leakage power we need to know why the leakage power is an issue. Actually we need to know. So why the leakage power issue is there? So we can see here the leakage power is becoming a large component in the total power dissipation. How I'm saying in this sense, you can see in this figure the x-axis which are showing as a technology actually. Here we are having the various technologies from this, like this is like 250 nanometer technology, because we are talking about deep submicron. Okay, deep submicron technologies. 250 nanometer, this is 180 nanometer, then 130 nanometer, this is 90 nanometer, this is 70 nanometer. You can see. So in this you can say what will be the power in watts you can see. So when you are working on, or when there's again 250 nanometer technology, you can see your the leakage. So this portion, is a leakage power, then this portion is a active. Okay, so it is will be active. How much it will be active, how much it will be leakage. You can see here when 250 go, the leakage is very less actually. As the technology grows, you can see the leakage component is very high actually. So that is why in the previous classes we seen, as the technology improves, the leakage will be very high due to so many different reasons. I said, like one of the very important reason I said, like what, your gate oxide, that is a thickness of the gate oxide. That is the one simple example I said. Next thing is here, that is why I said the leakage power is becoming a large component in the total power dissipation. The total power dissipation in the sense what? The total power dissipation, how can I say the total power dissipation? It's a combination of P static and P dynamic actually. Okay, so here the P static actually we studied the leakages. P static. So the P static in the sense your leakage. This is nothing but your leakage. So what is the leakage? Actually, these are the leakage P static plus the dynamic power dissipation. This is short circuit. Then I can say what is the next step? Short circuit power dissipation. Then switching power dissipation. Then I can say leakage power dissipations, right? This is the P static. Also one more is there. So adding all these things only will get the total power dissipations. Now here the total power dissipation is very large, adding to all these things. Then here the reduction of runtime leakage power is very important, because when the circuit is working in condition, we need to reduce the leakage power. That is also one of the very important factor. But normally the leakage will happen during the ideal state when the circuit is off condition normally. So now let us see how we are going to see as like the leakage power limit and the VT. The VT is nothing but the threshold voltage. How the threshold voltage will play a very important role in the leakage reduction. We can see here as the technology grows here, you can see the technology is growing in terms of micrometer we given. It is 1.5 micrometer, then the 0.7 micrometer, that is 70 nanometer, that is 35 nanometer. You can see 35 nanometer, it is 18 nanometer, it is 0.18 nanometer, 180 nanometer, sorry. So 180 nanometer, this is 90 nanometer. So it is going like this. Now you can see what is the leakage power here in terms of percentage variation. So as the technology grows, you can see your leakage power getting increasing, but at one point of time we must to stop the growth of the technology, because it's increasing more. Like you can see here at this point we must reduce. Actually still the working is going on. That is why you can say as the technology grows, the leakage power also will be increases. Now here the one of the very important, the key parameter for for leakage power is nothing but the threshold voltage scaling. Threshold voltage scaling. So before study about the threshold voltage scaling, we need to see about the threshold voltage, how it will play a very important role in the leakage. So now you can see in this graph we are showing this is about your threshold voltage in terms of volt. Then here we are having the performance like the normalized delay. Here we are showing as like kind of subthreshold leakage. That is nothing subthreshold leakage current. To normalize subthreshold. Okay. Now you can see this blue color which I was showing, this one. This indicates delay. This is indicates subthreshold leakage action. Now you can see as the threshold voltage increases, I can see, or I can say as the, because this is nothing but we need to reduce, correct? As your threshold voltage reduces, we can say like this, okay? As the threshold voltage reduces, what is happened? The delay also will be reduced. So I can say the performance will be good, correct? No, you can see this. As the threshold voltage is reduces, then the delay also will be get reduces. The delay will be reduced. If the delay is reduced, what about the performance good, we can say. This is performance wise, okay, the performance is good. But you can see what about the threshold leakage, what will happen? As you reduce the threshold voltage, what happened? Your subthreshold leakage current, you can see your subthreshold leakage current is increases. So that is why I can say we need to compromise the factor, like the performance, the delay will be reduced. The delay is reduced means, so it's good. But what about the leakage? The leakage will be very high. You can see here the leakage will be in terms of 10 to the power of 3. Actually, it is the meaning of 10 to the power of 3 actually. So as the supply voltage is nothing but like VDD. Okay. As the supply voltage we can say, as the VDD we can say, as the VDD is reduced power dissipation, that is what we can say, as a VDD is scaled down to reduce the power. So we can do simple, I can say, if you want to reduce the power dissipation, even you can reduce the VDD also So for power dissipation, power to reduce the power dissipation, then also what you have to do, so VTH, so at this case what will happen, as VDD is reduce the power dissipation means the threshold voltage also will be reduced. But if you are reducing the VDD, then if you are reducing the VT, then automatically what I can say, the power dissipation will go high. Actually, keep it in remember, VDD if you are reducing, when the threshold is reducing, then the power dissipation will be more. That's very simple. I can say, as you know that the threshold voltage, what is the range of the threshold voltage? So we know the formula, already we know that, right? That is like a 0.2 divided to, I can say, zero point 0.5 VDD. I can say this 0.2 only I can tell as this 0.2 only I can call as a low threshold voltage. This one I can call as low threshold voltage. This I can call as high threshold voltage. Okay, now take an example. VDD is equal to 5 volt. Then what about the VTH? The VTH is equal to 0.2 into VDD. So it is 1 volt. Next, VD I am reducing. Okay, as I said here, no, VD reduce. Okay, I will reduce the VD by 3 volt. Then what about the VTH now? If the VD is 3 volt, then I will get 0.2 into 3, that will be zero point 0.6 volt. Your VTH also will get reduced. But the problem is, if you keep on reducing the VDD as well as the pressure also get reduces, then they can have the power dissipation will be very high. That is what we can say here. The threshold scaling, a very important factor here. As the threshold voltage will be reduces means, if the delay will be reduces and the leakage will be increases if you reduce the threshold voltage. So your low threshold voltage, this will provides the high performance always. So low threshold voltage will provides the high performance, that is low threshold voltage means this will be your low threshold. But the high threshold voltage will reduces the sub threshold voltage. Keep it in mind. These two concepts is very important. So when I am using low threshold voltage, then your delay will be increased. You see this? Okay, when you are using low threshold voltage, the delay will be increased, but the leakage will be reduced. If the leakage current is reduced, then automatically what will happen? So that is the meaning of that. Your threshold on low VT means it will provide the high performance. Okay, this is the low VT. Sorry, this is the low VT. This is the higher VT. This is the lower VT. This will be your high VT. Okay, so now for lower VT, it provides for higher performance. This one, higher VT will reduce us the sub threshold leakage. So this will be improved for low VT. This will be used when used for high VT. So it is important when you are going to use the circuits like two different threshold voltage you need to use. But when you are going for the fabrication, when you put into the fabrication normally, so the manufacturer only will set the threshold voltage. So how they will set the threshold voltage? Adding their doping concentration levels. But when you're going for a device like putting the substrate, then after the diffusion, like adding the concentrations, like which concentration, the doping concentration, they will fix the threshold voltage, right? So now there only I'm saying, so they need to fix it like for two different circuits, like two different threshold voltage. But what about the cost? Two different threshold voltage, if we need, then the cost will be high to fabricate the IC in the sense to fabricate the ICs. So that is why we said here which is low, which is high. We already given. Now you can scale down the threshold voltage for low voltage, that is for low power circuits. Next, you can scale up the threshold voltage without affecting the performance. This is one of the very important thing. If you want to reduce the leakage power, the one important factor is the scaling of VTH. Then the another one more factor also is the later we'll study, that is VDD, that is power supply scaling. These two scalings are very important, VDD and VTH. Now here, if you want to fabricate the multiple threshold, that is why I said here, right? Here you got it. The two different voltage means are multiple fabrication if you want to do. So here the fabrication of multiple threshold voltage can be done by following ways. Say example, the first one is nothing but multiple channel doping. So when I go for multiple channel doping, what will happen? Like you need to increase the doping concentration. Increase the doping concentration. Okay. If you increase the doping concentration, what will happen? Your threshold voltage will be increases in terms of millivolt. The multiple channel doping in the sense, you see, like in your channel will have the doping, like adding the impurities, the doping concentration. So keep on, if you increase your concentration, so the doping concentration means we may write as NAND, acceptor and donor concentrations, right? Then multiple oxide thickness, this is a one more way to keep for a scale for a threshold voltage, the multiple threshold, that is multiple oxide thickness. So here multiple oxide thickness, so what we have to do, we need to reduce the oxide thickness. Okay, we need to reduce the oxide thickness in terms of what? Nanometer actually. So in terms of nanometer, that yields the threshold voltage will be reducers. See here, what will happen? If you want to increase the threshold voltage, you need to increase the doping concentration. If you want to reduce the threshold voltage, you need to reduce the oxide thickness. So at the same time, you need to keep, or we should maintain the constant aspect ratio. They will call like R. What is going to be aspect ratio? The aspect ratio is nothing but the ratio of channel width to the channel length. That is W by L. That is called as aspect ratio. Then third one is multiple channel length. Multiple channel means that's like the channel will be increased. Like if you are increasing the threshold voltage, or I can say like there is a small variation in the channel increases, small variation. If you increase the threshold voltage, there will be a small variations in the channel also. Then multiple body bias actually. So the multiple body bias in the sense, normally as you know that body bias initially it will be 0, as you know that, right? When the systems or when your transistors are connected in series like this, then you need to keep the body bias. See, this is the one body, this is the one bulk, this is the one bulk. So this and this and this, so I can say substrate, some simple B1, B2, B3. So I'll have the last transistor. If this is a ground example, then this will be connected to ground. So I can say that B3 is 0. Okay, but simple I can say that threshold voltage will be different. Here I will say something called as VTH1, VTH2. So these are some body bias voltage for body, like not VTH1, sorry, B2. Here I mentioned 0 is connected. I can say this will be like 1 volt, this will be like 2 volt. As you know that earlier we studied the body effect. What is the body effect? The body effect is nothing but during the reverse bias, like if your bulk potential is increases more and more negative, then your threshold voltage will be increases. That is nothing but simple I can say. If your bulk source voltage is increases, then the threshold voltage will be increased. That effect is called as body effect. Okay. Now, next what we are going to study, we are going to study about here the leakage power or leakage reduction techniques. So here we are having all the leakage reduction techniques will be classified into two categories. The first one is, as I mentioned earlier, it's a standby leakage reduction. Then second one is runtime leakage reduction. There are two categories. So first we'll study about the first category, that is standby. Standby leakage reduction. Okay. Okay, fine. So now standby leakage detection techniques. What are the different techniques we are having? Totally, the three techniques are there. The first technique is transistor stacking. Then the second technique is variable threshold voltage CMOS. So by short, I can call it as VT CMOS. The third technique is multi-threshold voltage CMOS. By short, I can call it as MT CMOS. So next, for same the way, second as I mentioned, for runtime leakage reduction technique. Having the first one is dynamic VDD scaling. The second one is dual VTH assignment approach. Then third method is dynamic threshold scaling, threshold voltage, that is VTH scaling. Okay. So now what I will do, we are going to study about the first. That is nothing but standby leakage reduction technique. In that, we are going to study about the first technique. So what is the first technique actually? The first technique is nothing but transistor stacking. Okay. Now you see, for transistor stacking, we took the example as 4 input NAND gate. We took the example of 4 input NAND gate. You can see this will be your PDD. It's a PMOS. So this is A, this is B, this is C, this is D. Then same A, B, C and D. The output will be taken in this output. Okay. Now you can say what is this stacking? Transistor stacking. When the transistors are in series in connection, especially in the pull down network. Why? Because the pull up network here in the NAT gate, it's like it's a PMOS, totally all are PMOS only. So any one transistor, if it is on, then there will be a flow of voltage to the output actually here will get. Okay, don't worry about this. So here we are going to talk about the stacking. Means when more than one transistor is in series in a CMOS circuit, then the leakage current has strong dependence on the number of turned off transistors. That effect only we can call as stack effect. So in your CMOS circuit, the leakage current is strong dependence on the how many number of transistors off actually. Based on the difference, that effect only can call as stack effect. So now in this example, what we are going to do, to put in elaborate way, we need to assume body effect is 0. Okay, in this assume body effect is 0. If I assume the body effect is 0, so now what I am going to do, we are going to do something like here, some 3 mechanisms will be there in the transistor stacking. You can see here what I am going to do in the sense, say example, let me take the example as here you can see the same diagram I'll put here. A, B, C, D. This is the portion taking the output actually, right? Now we can see in this is connected to ground. Okay. Now you see, what about this potential? You can see I'll put a potential here. See this potential. Okay, we need to know about these potentials. Here the output is there. Now we are going to make an assumption as A, B, C, D all are 0 volt. When all the 4 transistors are in off condition, 0 means it is NMOS, it is off, right? So now we know that this is the bulk actually. Each and every transistor, very important, the substrate. Okay, so this I will call as the bulk is BB1. That is like bulk 2. Sorry, this is bulk 2. This is bulk 3, I'll say. This is BB4. But as we know that, what is the voltage I'll get at this point? We need to know. At this point, I'm having the voltage as 14 millivolt. At this point, I'm having the voltage as the voltage as 34 millivolt. At this point, 89 millivolt. At this point, 2.3 millivolt because it is in off-wind condition. So if it is off-wind condition, you can see this transistor, this one. This is actually the body. This the voltage, whatever the thing is 2.3. All these things which are shown here, it is at this point voltage actually. Okay, so now here we can say what will be the threshold voltage of this transistor. Say example, I'll make it as this is transistor N1, this is transistor N2, then transistor N3, then transistor N4. Then what is the threshold voltage for NMOS, for all the NMOS now? it will not be equal at this point. Okay, why? Because the bias what is VB. So here you can see at this point here, because this is not connected, your VB1 is not connected. So here this, if it is little bit in zoom way I will put, okay, this transistor, only that transistor I will put in a bigger way. This is your N2 transistor, that is B input. I am giving the 0 volt. Now this will be your VB2. Okay, this voltage is nothing but 8.9 millivolt. Then I am having this is connected. At this point the voltage is 3.4 millivolt. 3.4. Sorry, not 3.4. It's a 34. That is 89. Okay, 89 millivolt. Now you can see the threshold voltage of this transistor. How much? Like your body voltage. What is the body voltage of this? This is not connected. Means like by default, if you say if this one is connected to here, example, keep in mind, if this is connected to over there, then that meaning is this VB2 will be, so we'll have different threshold voltage will be there. So example, I will say for this I will say VT1, okay, this I will say VT1, this I will say VT2, threshold voltage 2, this I will say VT3, this I will say VT4. Your total overall voltage will be this. VB2 will be less than VTH4. Your bulb voltage will be less than the threshold voltage. Actually, but here at this point, if this is connected like this, then your bulb voltage will be, sorry, not less than, it will be greater than VTH4. So if I do in this way, then there is a chances of getting body effect. To avoid that, what I should do, what you need to do in the sense to avoid that, it's very simple. You need to take this connection. This is your B, right? To avoid that only, what you have to do in the sense, this is the bulk, right? This is the bulk, no? As I mentioned, this should be connected to VSS. If I do this VSS, your VSS is nothing but 0 volt, correct? Then what will happen? Your VB2 will be less than your VTH. Then, so then there is no body effect. So this is the difference actually you will get. So that is the reason when you are going for implementation, any implementation in this circuit, what you have to do in that sense, you need to make this as like this. You have to connect to like this, you have to connect. Here you have to connect. Everything you have to connect. Then you can avoid the body effect. So you can have, see, when all the transistors are off, the voltage drop. That's like this. The voltage will be like in this place will be 14 millivolt. Here it is 34 millivolt. Here it is 39 millivolt. Here it is 2.3 millivolt. So this is, see, it's keep on if all transistor. If any one transistor is on, say example AB it is on, extra things are off. Only this will be your leakage power. This is the voltage actually. So now go for in a practical case here, you can see what happened here. The diagram shows in the same diagram we took, we given, because we need to see on which input combination your leakage current is very high, because your leakage current will be varies based on your applying the input. If it is a 4-bit, this is 4-bit, right? Because 4 input variable, 4 variable in the sense will have around 16 combination, because it is a 4-bit input. Okay, so initially you will apply 0 0 0, then you need to apply maximum 1 1. So what is 16 combinations? So when you are going for 16 combinations, I cannot say in which combination you will get a less power, like a less leakage will get, or in which. So that is very important. You need to find out that actually for which combination you are having more leakage or which combination will have less leakage actually. So for that purpose only here we are showing here, you can see here we took a 3 bit actually. The example here we took as 3 bit. So here they are given the value 0 0 0 0 1 0 1 0 3 4 5 6 700. Okay, now when 0 0 input is when it's 0 0, what will happen? The Q1, this transistor, which transistor? When the input is 0 0 0, then which will be a leaking transistor? Which will be leaking transistor in the sense which transistor it is off, that is a leaking transistor. So what is the leaking transistor here? The leaking transistor is nothing but the transistor is in off condition. So that only is nothing but your leaking transistor actually. When you are going for 0 0 0, the Q4 Q5, this is Q4, okay, this is Q4, this is Q5, this is Q6, this will be your Q1, this is Q2, this is Q3. When I give 0 0 0, the Q1 Q2 Q3 will be in off state. Okay, this is the leaking transistor actually, because these three will be on, the P transistor will be on. So at that time, how much the leakage current you are having in the sense will have 0.095. See, very small amount of leakage current when all the inputs are 0, when all are in off condition. Now 001. When you go for 001 in the sense, now you see which is the leakage transistor here, 001. So 001, if I say the transistor, the Q1 and the Q2, correct, because one C transistor on actually. So this is the leakage. You should think, you may ask the question, why not Q6? It's not a leakage transistor because the Q6 directly is connected to out, so it won't leak anyway. Okay, so when, because this problem will happen when the transistors are in stacking means in the CMOS technology the pull down network are connected in series in connection. Always this problem will happen in the series in connection there only. This is the method to minimize your leakage. Okay, now I am giving when I go for 001 combination we are having 0.1925. When I go for 010 again 0.15. Same the way for the last value we are going to give 111, then automatically what will happen, the leakage will happen Q4, Q5, Q6 because this is all are on actually. When all are on, what will happen? The output will try to discharge over there. So there will be some leakage over there because the PMOS. Okay, so that will be. Now you can see when all the because the leakage will happen as I mentioned. So it is more important means what? When it is in the runtime also, when it is in the working condition also, it is very very important. I said now you see when it is 0 0, your leakage current is 0.095 nano ampere. When the inputs is 111, then you see how much it is. It is 9.410 nano ampere. But here you can see the highest leakage current is 99 times that of the lowest leakage current. Correct? No, the lowest leakage current. So 99 times actually of that we got 9.140 here. Okay, so now in this, so what are the three mechanisms we need to follow to do reduce that? That is why we said here. What are the mechanism in the system? Three mechanisms are there to reduce. So what are the mechanisms in the sense? First thing is due to the exponential dependence of the threshold, because earlier we seen current on gate to source voltage, the leakage current is greatly reduced because of negative gate to source voltage, that is VGS is negative. The VGS is negative. So simple I can say three mechanism. The first one is like the VGS, right? That is what the VGS should be negative. VGS should be negative means what? It is nothing but simple I can say VG minus VS the source. Right? No, it is like so. Even the your bulk also is connected to VSS only. So this should be negative. You should bring. It should be like a reverse bias. So at this case I can say that from the previous diagram the VTH1 will be less than your VB1. Same the way the VTH2 will be less than VB2 because the bulk voltage should be 0 for all the transistors. Very important, make a note. For all NMOS transistor, the VB is equal to 0. There is no body effect. So VB is equal to 0. So due to body effect, as you know that body effect, when it will happen, when the body effect will happen, when the VB is increases, correct now? So due to body effect, that is a reverse bias with effect from source. Due to body effect, that is the reverse bias with effect to source. Then what will happen? Your leakage current will be reduces. Then sometimes, that is why we mentioned here, the leakage current is also reduced due to body effect. So due to body effect also we can reduce the leakage current because all the body of all the three transistors is reversed bias with respect to the source voltage. Then as the source to drain voltage is increases, that is VDS for all the transistors are reduced. So the threshold current due to the Dibble effect also will be lesser. So these are some three mechanism. Next here we want to say that transistor, or it is also known as transistor self bias. Transistor self bias. Why? Because it's taking the self bias, self voltage, because your bulk is connected to the source, right? So it is taking self biasing voltage, it's taking. That is what we can say, this is self bias. So here we are having so many some problems also will be there. That is what already we discussed, the problems like if you are having a single gate, only one gate, then it's a trivial problem to find out the input vector. Means if you are having only one single gate, if you are having, then it's very difficult to find out the input vector actually that produces the minimum leakage current when the circuit is in standby mode actually. If we are having only single gate, then second thing is that if the circuit is very complex for larger circuits, for the larger inputs, then the finding the input pattern is very difficult. Because if I say example, if I say for circuits complex circuits, so the input vector which will produces minimum leakage current is a non-trivial problem here actually. So it is very difficult because for a complex circuit, if I go take 8-bit anyway, it is very difficult for us to find out which will provide a minimum leakage current. So only what you have to do for complex logic gate circuits and all, so we need to generate the input vectors randomly. You have to generate and apply to the circuit, then the leakage power dissipation will be reduced. Instead of applying sequence of inputs, sequence means in sequential manner, apply random order. So then automatically what will happen? Your the leakage will be reduced. So the input vector that minimizes the leakage current is selected. Then one more thing, the pragmatic approach that also will be eliminated to do the simulation of 2 power n combination, because if your n is large, because n is the number of inputs, right? So there will be pragmatic approach also will be there. That also will be eliminated in the simulations actually. There will be some small subset of all the possible states is evaluated for the leakage, that is for this leakage. So this is about the transistor stacking.